Hi, students. This lecture is over chapter 24, which is officially electromagnetic waves. Now, you see I've started off with a lot of things written on the whiteboard, and what this really is a summary of pretty much everything we've done so far. Now, this is a transition chapter. This is, and I'll kind of say this in a moment here, I divide this class into three parts. Electromagnetic theory proper, which really deals with electric fields, magnetic fields, forces, application of Maxwell's equations, so on and so forth. Then that takes us from chapters 18 through 24, and then chapters 25, 26, and 27 are optics, and then 28 through 31 we would call modern physics, right? And so now this is a transition chapter. You could hypothetically put this particular chapter into the optics category if you desire. This chapter could probably go either in electromagnetic theory proper or into optics. It turns out that optics actually is part of electromagnetic theory. All right. And so anyway, where are we right now? Well, I've written on the board all of the Maxwell equations that we know so far. We know that there are four Maxwell equations, at least I've been telling you that. And we've covered three of them. And there's also the electromagnetic force law. And I haven't written that up there because this board's already pretty busy. So now I've written these Maxwell equations not in the manner in which we study them, but I laid them out a little bit differently. Okay, and so we have Faraday's law of induction. I've written that in the left, upper left corner, upper left quadrant, if you will. And remind ourselves, Faraday's law of induction is really the last of the Maxwell equations that we study, but it's the first one I'm going to talk about today. That again is that if you have a changing current, if you have a changing magnetic flux, you get an induced EMF. So you essentially have an induced EMF that would be in this current, and so you would drive a current if it's part of a current loop. So essentially, if you, as I said in the experiments we talked about at the beginning of chapter 22, we had a loop that had no battery attached to it, and yet when the magnet was put through it, it induced an electric current. Essentially, what happened was it actually induced an EMF, an artificial battery, effectively was in that induced in that wire loop, or in that little circuit without a battery. An artificial battery is put there such that that as long as the magnetic flux was changing in time, that this current was induced. All right, and of course the magnetic flux is officially, we can think of it in a college physics style. We could just call it B dot A, dot product of the magnetic field and the area, if the area is perfectly flat and uniform, and the magnetic field is uniform. If the magnetic field changes spatially, then we'd have to divide the area up of the wire loop into little tiny areas. Each one has an area normal A sub I and a magnetic field going through it, and we would add up all the dot products of B sub I dot A sub I. And if we want to do a perfect job, we would invoke calculus. So again, this is the calculus version of Faraday's law. Instead of deltas, we take the limiting delta to be infinitesimal. So this becomes a first time derivative of the magnetic flux. And of course, the magnetic flux itself could be written as adding the calculus style. This is called a surface integral of B dot dA, the dot product of B with the differential area, and integrated so that you literally are taking, you can literally consider a continuous magnetic field and a continuous area. There's nothing discrete at that point. Then we have Ampere's law. Ampere's law says, well, you have a current distribution. So this is your I enclosed. You have a current distribution. You enclose that in an Amperian loop. You take the dot product of the magnetic field and the displacement vector. So you basically have displacement vectors these are really supposed to be differential displacement vectors. And these displacement vectors literally are all around. They are tangent to the Amperian loop, and they're all about the Amperian loop. You literally do this calculation, adding up all the dot products of the magnetic field and the displacement vector at every single point. So this I, again, is an index number, 1, 2, 3, 4, dot, 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 I. So again, you take the magnetic field there, dot product with the displacement vector, you add up all the way around the Amperian loop, and by a miracle, it's equal to mu naught, the permeability of free space, times the enclosed current, the current distribution that's enclosed by the Amperian loop. And of course, this can be expressed in calculus style. This can be expressed as adding up calculus style. This particular integral is called a line integral. This was a surface integral. This is a line, L-I-N-E integral. A B dot ds is mu naught I enclosed. Again, just adding the calculus style. This is the official way of writing these two equations. Now, if you look at these equations, you look at these two Maxwell equations, and it's kind of easiest to see with Faraday's law. I wrote it's a time-varying magnetic field yields an electric field. Now you might say, well, wait a minute. I thought epsilon was a potential. I thought it was in units of volts. It's the EMF. How is this an electric field? Well, the EMF would do what? The EMF drives charges basically because it forms a potential. We know that when you have a potential, there's an electric field that goes between the two equipotential surfaces, and so charges get driven. So electric field is hidden right here inside this this thing that's a potential. We know that epsilon's like we know that epsilon is like an E times a D, where E is electric field. So there's an electric field implicit on the left-hand side. And of course, we know the magnetic field is directly in the flux. So you change the magnetic field, changing magnetic field in time yields an electric field. Of course, this negative sign deals with Lenz's law of opposition. So changing magnetic field yields an electric field. Now, Ampere's law says that a time-varying, so here's a time-varying magnetic field yields an electric, electric field. And this actually is backwards. Sorry about this. And Ampere's law is a little harder to see, is that a time-varying electric field yields a magnetic field. So here, you're not varying a magnetic field in time. This is a spatial addition, a spatial integral. This varies in time. This is a time rate of change of the charge. And of course, if you have a charge distribution, you have an electric field. So implicit on the right-hand side is a time-varying electric field yielding a magnetic field. So I apologize for this misstatement earlier. So again, Faraday's law of induction, again, you have to see this you can actually see this explicitly using vector calculus. And I'm not going to even try that here. But again, Faraday's law of induction in the deepest sense says that a time-varying magnetic field yields an electric field. Whereas Ampere's law says that a time-varying electric field yields a magnetic field. All right, and so you see a beautiful symmetry in the universe. Now again, James Clerk Maxwell came around and did this very analysis. And these equations were already out there. But there was not electromagnetic theory yet. James Clerk Maxwell did something like this. He laid all the equations out and says, well, do we have a theory here? And he saw that, there's a beautiful symmetry in the universe. Again, this is the work done by James Clerk Maxwell. There's a beautiful symmetry in the universe. I have two Maxwell equations that essentially say that a time-varying magnetic field yields an electric field, and I have a time-varying electric field yields a magnetic field. Well, you look over here, we have a flux equation for electricity. We are essentially saying that the total electric flux through a charged through an object that has a charge distribution, or a contained excess charge, is equal to the charge enclosed divided by epsilon naught. So magnetic flux through a charged object equals the enclosed charge divided by epsilon naught. That's what Gauss' law tells you. Now, Maxwell was a devout believer in symmetry. He thought the universe should be symmetric. So for him, he believes that there is an equation that's missing here. He believes that there should be a Gauss' law for magnetism. Now, the question is, what would this look like? And again, I don't have very much space, but a Gauss' law for magnetism would look like what? I'd have a magnetized object. So I'm going to not put a picture here. So it would look something like, well, I'd have the sum over I. Well, let's see, it's a magnetic flux, right? Magnetic flux through an object. B sub I dot A sub I equals what? Well, if we had magnetic charge, let's pretend we live in a universe where magnetic charge exists. Then I would write, well, I'd write magnetic charge or magnetic monopole divided by, I don't know, some other constant, epsilon 1. I'm just making stuff up. Now, Q sub M would be magnetic charge. Or a magnetic monopole. If I can fit this in here. If they exist. I mean, again, pretending we live in a universe that has magnetic charge. Well, we do not live in a universe that has magnetic charge. Now, there were competing, I think at the time, a total of 5 competing electromagnetic theories. Maxwell's was one of them. Some of the theories assumed magnetic charge. Well, Maxwell, his theory did not assume magnetic charge. So if magnetic charge does not exist, and I want a magnetized object, I put a Gaussian surface around it, I get the magnetic flux, then what should the right-hand side be if magnetic charge does not exist? The right-hand side should be 0 because magnetic monopoles do not exist. And indeed, this is the final Maxwell equation. This is Gauss' law for magnetism. Magnetic monopoles do not exist. Total magnetic flux through around a magnetized object is 0. You want to write it the calculus style? You can do that too. You know, it would simply look like this. Surface integral B dot dA is 0. So there you are. And the other thing too is you can look at it this Maxwell equation, the Gauss law for magnetism, 2 ways. One way is a verification that magnetic flux does not exist. Another verification, I'm just going to say this, I'll write it a little bit later, is that remember, what is flux? Flux again is dealing with, would be magnetic field lines dot product with the area normal going everywhere. Remember, magnetic field does not, I mean, electric fields start on a positive charge and terminate on a negative charge or at infinity if the positive charge, say for instance, is isolated. But remember, magnetic field lines do not begin or end. And I'm very careful of my wording here. Magnetic field lines emerge from the North Pole and re-enter at the South Pole. So every magnetic field line that leaves a magnetized object comes back around and re-enters. So every magnetic field line that leaves a magnetized object at the North Pole comes back around at the South Pole. Altogether, if you add up all the magnetic flux, you'd get 0. So this is another statement that says that all magnetic field lines, either they emerge at the North Pole and they come back at the South Pole. Every magnetic field line that leaves the Gaussian surface about a magnetized object ends up coming back around and re-entering. So again, two ways of interpreting Gauss's law for magnetism. Number one, magnetic charge does not exist. Magnetic monopoles do not exist. Or the total magnetic flux is zero, in that every magnetic field line that leaves the North Pole comes back around and re-enters at the South Pole. This is it, folks. These are the four Maxwell equations. These equations, plus the electromagnetic force law, let me see if I can fit that up here, are the entire basis of every electrical and magnetic phenomena that you can ever imagine. So I'll just write Maxwell equations here. And of course, we have the force law. The magnetic force law is QE plus QV cross B. That's the magnetic force law. So you have five equations that govern every single electrical and magnetic phenomena that you could ever imagine. Everything from the two charges being attracted to one another, to two parallel currents attracting each other, to operation of electric generator, electric motor, a transformer, electric circuitry, you name it. Every single bar magnet on the refrigerator, the operation of electromagnet picking up junked cars, every single electrical and magnetic phenomena you can ever imagine is an application of one or more of these five equations and nothing else. These five equations are the absolute basis of electromagnetic theory. Now you might wonder for a moment, okay, you call these Maxwell equations, but I do not see Maxwell's name anywhere in these equations. Well, what it is that Maxwell put together the entire theory. There was no electromagnetic theory officially before Maxwell. Maxwell was the architect that put it all together. And by the way, Maxwell actually fixed up the Ampere's law. There's actually a term for what's called electric displacement in Ampere's law. I'm not going to talk about it here, but in many cases, the Ampere's law in more advanced books is oftentimes called the Ampere-Maxwell law. So actually, Maxwell does have his name on one of the Maxwell equations. And so this is Maxwell's theory of electromagnetic. This is Maxwell's electromagnetic theory. All right. So again, five equations. All right. So now let me kind of write these out in more compact form. Okay. So again, Maxwell's equations. The four Maxwell equations. Plus the electromagnetic force law. Explain every electrical and magnetic phenomenon. Every single one, no exceptions. Every electrical or magnetic phenomena is explainable and is an application of one or more Maxwell equations and the electromagnetic force law, period. Okay, so Maxwell amalgamated. So Maxwell basically derived the true electromagnetic theory. We already know, besides this, Maxwell also is also the author of the kinetic theory of gases. We talked about that in physics 1. The very first ever atomic and molecular theory known to humankind. And he also, besides these things, he also put forth a theory of color, and he explained Saturn's rings. So he is in any physicist's book in there with the top 3 physicists who ever lived. So the greatest physicists who ever lived were Isaac Newton, James Clerk Maxwell, Albert Einstein. Albert Einstein is the greatest of all. All right, and so again, this is James Clerk Maxwell. He only lived to be 47 years old. He was born the same year that Faraday put forth Faraday's law of induction. 1831. He died, unfortunately, way too early, 1879. Which, by the way, is the year Albert Einstein was born. So here he's born on the year that Faraday put forth his law of induction, and died the same year as Albert Einstein was born. All right. He's from Scotland. So, brilliant physicist, no doubt about it. Now, any of these things would, of course, made Maxwell one of the greatest physicists ever, but Maxwell's not yet done. All right. So Maxwell amalgamated what we thought were theories of electricity and magnetism, but then what Maxwell then said is the next topic. So Maxwell then said, let's take these equations and consider a special case. Let us have a case of no sources. I.e., no charges and no currents. In a vacuum. All right, so Maxwell's equations end up looking like what now? Well, Gauss' law of electricity. Remember, normally Gauss' law of electricity looks like what? Sum of all forces. So again, Gauss' law of electricity. Normally looks like the summation of all forces. Of all E dot E sub I dot A sub I. about a Gaussian surface is Q enclosed over epsilon naught. But we're assuming no charges. We're assuming source free, no charges, no currents. So in this particular special case, we're considering a special situation where there are no charges. So the right-hand side of Gauss's law for this special case will be 0. Gauss' law for magnetism is always the same look. That's always going to look like summation over I over a magnetized object of B sub I dot A sub I equals 0. Faraday's law is also not going to change, except, well, there's not going to be an induced current. Of course, there's no currents, but there still will be an EMF. We can just make sure we have an open circuit so as to not have currents, right? You're still going to have an EMF. Whether you have a closed circuit or not, it's like you have a battery. If the switch is open, you still have that battery, right? You're still going to have an EMF, negative delta phi sub B with respect to T. So again, Faraday's law is not going to change. You just have to not have a circuit, not have a closed loop so that you don't have a current. Remember, we don't want currents. And finally, Ampere's law. What's it going to look like? Well, Ampere's law, again, looks like the summation of all B sub I is going around the Amperian loop dot S sub I. And normally, it's what? Mu naught I enclosed. Mu naught times an enclosed current distribution. Well, again, we're assuming no currents. So again, Ampere's law, the right-hand side of that goes to 0 as well in this special case. All right. So Maxwell pointed out, I want to consider a special case of source-free environment in a vacuum. Okay. Now, when he did that, he then went off and used advanced vector calculus and combined these 4 equations. All right, and so the next thing that Maxwell did is combine the 4 equations. So I'm gonna erase them. So Maxwell then combined the 4 Maxwell equations for this source-free problem. And derived the following 2 equations. Using, a lot of vector calculus. Calculus 3 stuff. All right. So what he derived, that's going to look a little alien to you at first, but I'm gonna do this in one. I'm gonna write these in one spatial. So I'm gonna consider one spatial coordinate x and the time coordinate t. And again, these 2 equations may look a little foreign, but you get the following. You get what's called a second partial of the electric field with respect to x equals 1 over mu naught epsilon naught second partial electric field with respect to time. And let's be really explicit here. Electric field, again, right now, I'm considering a reduced case. This really is a 4-dimensional problem. But I'm just going to consider the electric field right now is only a function of space of x and t, okay? So again, to make things a little more simple, 1 over mu naught epsilon naught, what's called the second partial electric field of x and t with respect to time. And right next to it, we can write the second partial of the magnetic field of x and t with respect to x is 1 over mu naught epsilon naught second partial of the magnetic field as a function of x and t with respect to time. Okay, now these equations probably look very weird to you. Now, as I've told you many times, that, we talk about differential equations, I just will talk to you and say, well, the highest level math class taught at our school is differential equations, right? And I've mentioned differential equations a few times. That's the highest level math class you can say to school. You can take it to school, and I just call it differential equations. I'm really being a little bit sloppy when I do that. I really ought to call this ordinary differential equations. All right, so actually we would refer to any different differential equations that you take in that class as an ordinary differential equations, or an ODE, ordinary differential equations. That's the highest level math class that you could take at TCC. This is higher than that. If you go to the next higher level math class, you take what is called partial differential equations. And that's what these are, and they would be referred to as a PDE. Okay, now, not all partial differential equations courses are the same. Some are different than others. But light right here. All right. Okay. Trying to adjust this light to go away. All right. So not all partial differential equations courses are the same. All right. And so the one I took was actually, it just so happened to be that the professor, the math professor, happened to be a physicist, and so he this is sideways. Yeah. That's all right. He happened to be a physicist, and so a lot of physicists wanted this class. So he actually there's a at the University of Puget Sound there's a course called Topics of Applied Math, and so a mathematician can actually make this class whatever he or she wants to make it. And so Professor Martin Jackson is his name. He's a great professor, one of my favorites. He decided to make this a partial differential equations class, which was great because it served a bunch of physicists. And so every partial differential equations class is unique. But one of the things that they actually all cover are 3 equations, 3 major famous equations. All right. So again, let's kind of talk about these. I'll keep these written up here. So every partial differential equations class covers every partial differential equations course is unique, but they usually all cover three famous partial differential equations that occur in physics. They are Laplace's equation, which is pretty much ubiquitous in physics, the heat equation, and the wave equation. Now, the heat equation governs heat diffusion, and they're all partial differential equations. Any trained physicist, and particularly someone with the supreme talents that Maxwell has or had, would recognize these two equations right away as wave equations, whose solution is the wave. All right, so these are wave equations. He combined Maxwell's equations in source-free space, and he's finding out that the electric field and the magnetic field propagate as waves. All right, now in general, the wave equation looks like what? Again, in one dimension, or one spatial, one time dimension, a wave equation in general looks something like this. So in general, with one spatial dimension x and one time dimension t, and a time dimension t, a wave equation looks like second partial of f of x and t with respect to t is going to be v squared. Second partial f of x and t, oops, this is with respect to x, sorry, with respect to time. Now, one thing, and of course, the answer to this is going to be the solution. You always want to answer your question is, what's the solution? Well, the solution to, just like with any other differential equation, the solution to this wave equation is the following. It is given as a times the sine of kx minus omega t. Now, I want to point out a couple of things. This is the solution. What are these funny looking d's? These are soft d's. These are called partials. All right, so a partial is basically, this is the partial operator. Partial differential. Operator. It's like a soft D. And what it does is it says, well, it's quite simple. You're taking a time rate of change, or you're taking a change or we call it a slope, if you will, a second order slope of a function that has two variables, x and t. So when you do something like this, you're saying, I'm taking a second. I know that this function f is has two independent variables, x and t. I'm going to leave t constant and just take the second partial, or take the second order slope on x alone. Just worry about the x variable, leaving t constant. And this one says, I'm going to leave x constant and just take the second order slope of t. So when you do something like that, you're just basically recognizing that you have a function that has more variables in it than just one. It's a multivariable function. And so you're just taking terms. This one says, I am taking the second order slope of f with respect to x, leaving t constant. And this one's saying I'm taking the second order slope of f with respect to t, leaving x constant. That's all this is saying. And of course, you can only imagine if ordinary differential equations is hard, partial differential equations is even harder. But what's nice is that when you see a form like this, you automatically know that's a wave equation. Maxwell knew that. Maxwell knew that first of all, that the electric field and the magnetic field must obey a wave equation. Now, something else that's important to note here is that this v squared, this is the propagation speed of the wave. In general, whatever is sitting, whatever is in front of this time, this time differential term is the propagation velocity squared. So if you take a look at the electric field and the magnetic field, that particular factor is 1 over mu naught epsilon naught. So we're saying that mu naught epsilon naught, 1 over mu naught epsilon is a square of whatever the propagation speed is of these waves. Well, that's interesting. Let's see what that would be. So again, what this tells us is that the electric field and the magnetic field propagate as waves. So what Maxwell showed is the electric field and the magnetic field propagate as waves. With a propagation speed of v equals 1 over the square root of mu naught epsilon naught. What could this possibly be? Let's work it out. So I have v. Okay, I have 1 divided by, so what is mu naught? Mu naught is the magnetic permeability of free space. It is 4 pi times 10 to the negative 7 Tesla meter per ampere. All right. And I have the permittivity of free space. Again, this is a magnetic constant. Here's a pure electric constant. And that's 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. I put all this in a square root. 1 divided by that. I find out that V has an interesting value. It's 299,792,458 meters per second, or the speed of light. What James Clerk Maxwell just did with this derivation is complete the greatest amalgamation in the history of science. He not only showed you that electricity and magnetism are not separate fields of study, but they are all they're both manifestations of the same electromagnetic field. He just showed you here that not only are all electrical and magnetic phenomena described by Maxwell's equation and Lorentz force law, but all of light, all of optics is also described by Maxwell's equations. He amalgamated the fields of electricity, magnetism, and optics, or light. Every single electrical, magnetic, and optical or light phenomena you could ever imagine is a manifestation of the electromagnetic field. It all is described by electromagnetic theory. This is one of the greatest accomplishments in the human race. This right here. This amalgamation. You know, if Maxwell wasn't already the greatest physicist, here, this is just unbelievable success. Right? So he literally, so literally, the work that Maxwell just performed shows Maxwell showed, or Maxwell was responsible for the greatest amalgamation in the history of science. Maxwell showed that all electrical, all magnetic, now all electrical, all magnetic, and all optical, all electrical, all magnetic, and all optical phenomena, or light, if you will, phenomena are manifestations of the same electromagnetic field. Now, I will talk about later on in chapter 27 that there are great debates about what light was. Is it a stream of particles or is it a wave? Maxwell showed, yea, verily, that it is a wave. Now, we're going to find out when we talk about quantum mechanics, that we're going to find out later on that it's also a particle. But at this point in time, 1870-ish, I think is when he publishes, 1869, 1870, he publishes Electromagnetic Theory, is that light was unarguably a wave. And the book was closed on that. And what's really interesting here too is you look at the speed of light. You see the speed of light, 1 over mu naught epsilon naught square root. I mean, that's really amazing. Epsilon naught is a constant of the universe that really came out of the work done by people like Coulomb. And talking about understanding Coulomb's law, understanding electric fields, pure electricity, and mu naught came out of the work done by Oersted and Ampere, understanding magnetism. You take this magnetic constant and this electric constant, you multiply them together, take the square root, take the multiplicative inverse, you get the speed of light. You get something that's purely a property of light. So that is unbelievably amazing. Now, this is all done by Maxwell, and then so again, this we now have a full-blown electromagnetic theory. 1870, roughly, we have a full-blown electromagnetic theory at this point. All right, and we're going to transition into optics in the next chapters. But again, as I've said before, our class is divided up into I would call electromagnetic theory proper, I would classify this as chapters 18 to 20 through 24. This deals what electric field, magnetic field, electric force, application of Maxwell's equations. Then we go into what I would say is optics. And that's going to be study of light, mirrors, lenses, things like that. That's chapters 25 to 27. So I guess it's going to be reflection, refraction, lenses, mirrors, things like that. Totally different look and feel, even though optics is really, as I just said, a manifestation of electromagnetic theory. And then the third part of this class I call modern physics. That's really the physics from about 1900 onward. All right, and that's chapters 28 through 31 in this class. That's going to be special relativity, quantum theory, atomic physics, nuclear physics. All right. So we're in a transition chapter. All right, so we're transitioning into what we would do is study of light. But we're going to realize that light is one part of what we call the electromagnetic spectrum. All right, so we have electric fields, magnetic fields propagating in space and time. Let's look at this now. So first of all, like any other scientific theory, you have to apply experiment to the theory. All right, and so let me next talk about the experiment that was done to verify the work of Maxwell. All right, and so I need to open up my book here. I meant to open it up beforehand, so give me a moment. All right, come back. All right, here we go. It's gonna take me a minute. Okay, so we have a full-blown electromagnetic theory now, and predicted by Maxwell. This is purely a theoretical exercise. I mean, Maxwell has what at that point is thoroughly believed to be the true electromagnetic theory. But we need to, we certainly understand how electrical and magnetic phenomena are all explained. But does this really explain electromagnetic waves? Is he correct that electric fields and magnetic fields propagate as waves? All right, and so the person who took on that task was none other than a German physicist by the name of Heinrich Hertz. So I'm going to talk about him. All right, so really briefly, so a brilliant German experimentalist by the name of Heinrich Hertz in 1887 performed an experiment that proved that electromagnetic waves do exist. So German physicist Heinrich Hertz, German experimental physicist, we named the unit of frequency after him. Heinrich Hertz. Experimentally verified the existence of electromagnetic waves and that they travel the speed of light. So he did this in 1887. Heinrich Hertz was a brilliant German physicist. Maxwell had already passed away. Right, Maxwell was already gone for 8 years at that point in time when this happened. But this verified experimentally that Maxwell's theory is indeed right, indeed correct. So let's talk about Hertz's experiment. I'm going to share my screen here. Okay, so you see a little a diagram in front of you, and what this is showing, and we just got done studying RLC circuits. In fact, you see on the left, I'll try to put my mouse here, is an RLC circuit, and you see a resistor, capacitor, an inductor. You see the variable, the power supply, and what Hertz did is he set alongside of it another circuit that did not have a battery. And he made a transformer by putting two inductors together. So again, remember, you can make a transformer. A transformer is essentially magnetic flux going through loops. I showed an example that was Faraday's example of having a ferromagnetic core where magnetic flux goes, is trapped in a ferromagnetic core, and it goes from one set of one loop, one coil to another coil. Well, these are just two coils that are put together and created a transformer this way. And so you see these two transformer loops next to one another. And what happens is because this is a time varying current, this induces current in the other loop. And what happens is that a very high voltage spark is created. Now, Hertz set up another loop just like this spark loop, another spark loop on the other side of the lab. And he connected it with a tuner, like a radio tuner, same kind of tuner you'd have with a radio. And he set that tuner, again, he set it to the same resonance frequency. We just got done talking about resonance. Remember, resonance is omega naught is 1 over the square root of LC. Well, he set that tuner to be such that the electrical properties of the receiving spark loop were set to match the electrical properties of the one that is transmitting. And it turns out that he generated a spark in the main loop, the main spark loop that is being driven directly by the RLC circuit, and across the lab, a spark occurred in the loop that was attached to the tuner. Well, he was able to show he was able to show physically, that you cannot argue that there is an electromagnetic wave there. There's a spark being caused, and he was able to tune this little radio of his such that if he didn't tune the properties right, there would be no spark. He tuned the radio to the same resonance and showed that he was able to set a spark across the lab. This was the very first ever electromagnetic wave set in a laboratory. Probably the very first ever man-made, I would say the very first ever man-made electromagnetic wave. At least one that by design. Faraday was utilizing very high voltage experiments that were giving off electromagnetic waves. I don't think he was really aware that he was doing that. X-rays, in fact. And so he was doing that, but not by design. Hertz was sending out waves by design. So he showed through this experiment that not only did do electromagnetic waves exist, but they also travel at the speed of light. All right, and so this is the experiment done by Hertz to prove the theory of this gentleman right here. Again, this is OpenStack, so show you a picture that is complements of OpenStax and the photographer who took this picture. This is James Clerk Maxwell. So again, compliments of G.J. Stoddart, who took the picture. But again, this is an OpenStax. This is the great James Clerk Maxwell. He is the person who is responsible for the electromagnetic theory, the great amalgamation of electricity, magnetism, and optics. And again, this is the experiment performed by Heinrich Hertz. All right, so this is, again, a great success in humankind. The entire radio industry, television industry, radar, military radars, or radar to, that's used for weather systems. Everything that we do with electromagnetic spectrum, microwave oven, everything, all of this technology is all from the work by Maxwell and this experiment by Heinrich Hertz. All right, so again, incredible successes, in just a course of, about 17 years, really. Maxwell's theory came out in 1870, and Hertz's experiment was 1887. All right, now, one of the things that we want to try to do is we say, okay, well, let's apply the concept of electromagnetic sending these electromagnetic waves. Let's see. How do we send them in a systematic way? Here's another set of pictures from OpenStax, and what you see is a long antenna wire. Okay, this antenna wire is as such as it drives charges periodically. So if you take a look at the first picture, we call it picture A. In picture A, you see that you have charges driven to their maximum extent. Negative charges are all driven to the top of this wire. This is nothing but a conducting wire. This is an antenna. This is a transmitting antenna. Just a long piece of metal that's being driven by a sinusoidal EMF. All right, so in picture A, you see that the negative charges are all driven to the top of this wire, this antenna, and the positive charges have been driven to the bottom of this antenna. Now this antenna this EMF is changing the position of these charges over time. Now, so picture B shows what happens when the EMF is varied such that there is no charge separation. The charges are brought back toward the center. There is no charge separation in that point. And then picture C shows the exact opposite. Shows instead of having all negatives pushed to the top and all positives pushed to the bottom, now you have all positives pushed to the top and all negatives pushed to the bottom. And of course, the electric field always goes from positive charge to negative charge. And so as you see, the electric field vector is oscillating in a plane with respect to time. And so it's oscillating and it's being propagated out at the speed of light. So at an initial time, you see electric field vector as a maximum positive electric field. Over time, it gets smaller and smaller. And so here, that electric field gets propagated out. It's going out at the speed of light. It's gone, right? By the time you get to the second picture, that same electric field that was generated because of that initial charge separation is now away from the wire out here. Now, the electric field vector at this point is 0. So electric field, the magnitude of the electric field vector has gone from a maximum going, from top to from basically maximum pointing up to 0. And every single time you see electric field vector, it propagates out. And then picture C shows now you have the charge separation going the opposite polarity. And so eventually by the time you get to picture C, you see the maximum electric field that's now downward. And this continues. Again, that gets propagated out. And it continues, and they go back to zero again, and they go back to where they were again, to the maximum upward electric field direction, or the maximum magnitude in the upper direction, upwards direction. So again, this is the electric field being propagated as a sine wave. So way out here to the right, if I look at picture D, way out to the right was that initial electric field where we have picture A. It's now long gone. It's been propagated out. What has happened since then is the charges came down. So electric field got smaller and smaller because the charge is still you had negative charge above the in the upper part and positive charge in the lower part. But again, the electric field is getting smaller and smaller because the charges were coming back together. By the time you got to this zero right here, now the charges were in the center, and there was no electric potential. EMF is zero. There's no electric field. Then the polarity shifts, and over time, the electric field gets pointed in a negative direction. Magnet gets larger and larger and larger until you have the maximum downward displacement right here. This would be corresponding to that picture C. And then the charges are coming back together again. So you still have a downward electric field, but eventually they come back together in the center. Again, the EMF goes back to being zero. And then it goes back periodically, and the charge separation then goes back to the way it was before, where you had negatives in the upper portion and positives in the lower portion. And then you end up having a larger and larger electric field magnitude until, again, you reach that same maximum magnitude with electric field pointing up. You're going to see this, and again, the electric field propagates away. The electric field, you see this described in this plane, the electric field vector in this plane. This is a vertical plane. Electric field vectors will live in this vertical plane. So again, at the initial time, we're looking at picture A. We had full charge separation, all the negatives as far to the top as possible, all the positives as far on the bottom as possible. Electric fields always go from positive to negative. So electric field is its maximum amplitude going upward. Again, the larger the separation of charge, the greater the amplitude of the electric field, and it's pointing upward. Now the charges are getting closer and closer together. Still having positive charges on the upper portion, negative charges on the lower portion, but because charges are closer together, the electric field magnitude gets gradually smaller and smaller. Eventually, the EMF, the driving EMF, goes through a zero, which means that it is no longer separating charge. Again, at that point, there is no electric field, so it's zero. And then the polarity of the EMF switches periodically, as it always does. And now you have charges being separated the other way. Negative charges being pushed to the bottom, and positive charges being pushed to the upper portion. So electric field becomes gradually larger and larger magnitude, but pointed downward. And it gets to a point where the charge separation is maximized. Now the positive charges are as far to the top as possible. Negative charges are far to the bottom as possible. And the electric field is at a maximum magnitude pointing downward. And then the charges are coming back together again. Still with the downward polarity. But the charges, the negative charges are still on the bottom portion, the positive charges are still on the upper portion, but they're getting closer and closer together until they get back to zero. And then the EMF is temporarily zero. And then the EMF switches polarity yet again, with the negative charges being on the upper portion, the positive charges being on the bottom portion, just like in the first picture, until you finally get that first picture. You get back to that picture A again, where you have the maximum separation of positive charges on the far bottom and negative charges on the far top. where you have the maximum upward pointing electric field, then everything happens all over again. Every single instant of time, an electric field of a particular, of that current magnitude, that magnitude and direction is propagated out at the speed of light. So over time, this sinusoidal electric field is being propagated out. And these electric field vectors are in the same plane. While this is happening, again, you're talking about electric field, you're talking about charges moving. Moving charges is a current. So again, when you have the maximum movement of charge, like in the first picture, you have, Faraday's law, Ampere's law says what? I put my thumb up along the direction of the current. Now, of course, if the charges, if the electric field, like in this first picture here, electric field is pointing down. So what's going to mean the current is going to point up. Again, we're talking about electrons. And so if I put my thumb in a direction, up along the wire, my fingers are going to curl around the wire. That's Ampere's law. And so you see that the magnetic field will be in a plane perpendicular to the electric field. And when the current is a maximum, with the charge separation, charge polarity, polarization in one direction, the magnetic field will also be a maximum. Electric field will also be a maximum magnitude. And then when the charge separation is zero, it means the current is zero, and the charge separation is zero, so both the electric field and the magnetic field will be zero. And then when the polarity changes, well, not only does the charge polarization change, or the electric field vectors, as I said before, flip, but so also does the magnetic field. And when you have maximum charge separation of the opposite polarity, again, you're going to have a current of the opposite direction. You're going to have a maximum magnetic field that's in the opposite direction as the original magnetic field. And again, the charges will go back, get closer and closer together. When the EMF has gone to zero, the current will also be zero. So the magnetic field will be zero. And again, the polarity will shift. And as the charge polarization goes the way it was before, the magnetic field will be constantly growing and growing, and it'll reach a maximum just like it did initially. Maximum, current in the original polarity, and again, so if you imagine if I describe, let's say, X going to the right and Y into the board and Z up along the wire, well, the electric field will be always propagating. The electric field vector will always be in what we call Z, parallel to the wire. The magnetic field will always be propagating along Y, and their direction of propagation will be X. So I can take a look at this last picture here, picture C, and I can, well, actually, what you get, you put them together. This is the electromagnetic wave propagating together. So again, I can define the electric field as being in the Z direction. I can define the magnetic field as being in the X direction. They're propagating out, we would say, the magnetic field in the Y direction, they'd be propagating out along the X direction. Again, you notice that the little C right here means this is the velocity of propagation out to the side. All right, and so let me kind of imagine this figure here. This is figure 24.7. And let me kind of give you an orientation here with respect to that figure. Okay, so we're looking at figure 24.7 OpenStax. What we saw, if I were to say, well, let's let this direction be X, and I'll try to draw this in a somewhat of a, here's my wire direction, we'll say Z, and we try to draw this so that it's perpendicular. This would be in a Y direction. All right, and so this would be my Y, so X, so this would be the positive Y hat. This would be positive X hat, this positive. It's supposed to be a three-dimensional picture. We see that the magnetic field is propagating along Y hat. the electric field is propagating along what I would refer to as Z hat. And the propagation direction is along X hat. That's the speed of light. There's your B equals C, speed of light. All right, they are mutually propagating. All three directions. It's a three-dimensional picture. The electric field is the electric field vectors, the magnitudes. They are in this particular picture. They're confined in the Y direction, what I call the Y direction. The electric field vectors would be confined in the Z direction, and the propagation, they propagate together, what I would call in the X direction. They propagate in a direction that's mutually perpendicular to the direction of propagation of both the electric field and magnetic field. The electric field and magnetic field are together constantly. When electric field is a maximum magnitude, so does the magnetic field. When they get smaller, so when the electric field has a maximum magnitude, so does the magnetic field. When they get smaller, and then they go down, then they come back, they're constantly propagating like that. Okay, they're constantly switching polarity. When the electric field vector switches polarity, so does the magnetic field vector. When electric field magnitude is 0, so is the electric field magnitude. They are both propagating together in a three-dimensional complex wave. This is a transverse electromagnetic wave. So the electromagnetic wave is transverse. So the electromagnetic wave is a transverse wave. Which means that the disturbance, or I would say the disturbance creating the wave is perpendicular, is in a direction perpendicular to the propagation direction. Okay, so this is a transverse electromagnetic wave, just like you studied in chapters 16 and 17 in physics 1. All right, so again, you have what's called a transmitting antenna. An antenna is how you get electromagnetic waves sent out. All right, and so again, as any other wave, electromagnetic waves also obey. They obey the same equation. Again, the velocity equation that I gave you for all waves. Remember, I told you all waves obey. Velocity is the wavelength times the frequency. All waves obey that. For electromagnetic waves, it turns out that that velocity is the speed of light. So again, the electromagnetic wave is characterized by a wavelength lambda, which typically would be in meters, and a frequency, an oscillation, or we'll say a frequency F, which would be in hertz, again, to honor Heinrich Hertz. All right, so like any other wave, velocity equal or speed equals lambda times f is always obeyed. That's true for sound waves. That's true for water waves. That's true for waves on a guitar string. Any waves that you can possibly see or any waves you can possibly observe, no matter what the source of the wave, they all obey C equals lambda or V equals lambda f. All right. Now, as we see, the electromagnetic wave moves together. So both the electric field and the magnetic field are mutually perpendicular to each other, and they're both perpendicular to a third direction, which is the direction of the velocity. Now, I talked about transmitting electromagnetic waves a moment ago. You also have the ability to receive electromagnetic waves. And so electromagnetic waves, we have, and so you have let's say, you have a radio station, you have an antenna at the radio station that emits electromagnetic waves, like we just got done showing. Well, you have an antenna at your house. Now, again, we used to do this more. Maybe on your car would be more appropriate because now everybody has satellite, right? But let's say you have the old style antenna. Well, that antenna is set to actually receive electromagnetic waves. All right. And so electromagnetic waves are transmitted by applying a variable EMF to drive charges or drive charge separation periodically in a long conductor called an antenna, called a transmitting antenna. All right. Your favorite radio station has such an antenna, has such a transmitting antenna. All right. So we showed how you can send electromagnetic waves. What about receiving them? All right. The transmitting antenna, we know not only do they exist, we actually know how to actually send them. Now the question is, how about receiving them? All right, so essentially electromagnetic waves carry energy away from their source. And again, all waves have energy. All right, so they carry away energy. And again, all waves such as sound waves, and waves on a guitar string carry energy. This is not a new concept. All right, so they do indeed carry energy. So an antenna for electromagnetic waves works in reverse. All right, and so so basically we have what are called receiver antennas. So there's transmission antennas and receiver antennas. Some military radar, a radar can actually both be a transmitter and a receiver. All right, so when it's either in receive mode or transmit mode, right? But receiving antennas, like in the ones at your house. So receiving antennas are designed, are specially designed to resonate at a particular frequency. All right, and so essentially, when you're receiving it, you, let's say, turn a channel or something. Well, what happens? Well, so basically, this energy, is being received by the electromagnetic by the receiving antenna, and it says pretty much all incoming electromagnetic waves okay, we're talking about the receiving antenna, accelerate electrons in the receiving antenna. Okay, and this sets up a standing wave. So really, what you had with the transmitting antenna was also a standing wave. These charges were bound. They can only go so far. They're going all the way to the ends, coming back to the center, going back. They're bound by the length of the antenna. The antenna sets up a boundary condition for these waves. So you get a standing wave also in the receiving antenna. I didn't mention that, but the transmitting antenna also, or the electromagnetic waves from a transmitting antenna were also standing waves. Well, anyway, you have standing waves. Actually, they propagated out. Never mind. But you have standing waves that are actually now in the receiving antenna. All right. Now, the radio or TV is switched when the radio or TV is switched on or turned on. When the radio or TV is turned on, electrical components pick up, so they're set to pick up and amplify the signal formed by the accelerating electrons. And the signal is then converted into audio and or video format. All right, and then now again, this is what happens to the receiving antenna. Now the let me erase this. All right, so we have the energy is carried by the waves from the transmitting antenna. The energy then oscillates or causes standing waves, accelerates electrons in the receiving antenna, and special components in the system will then convert these accelerating electrons into audio or video format. That's where we are right now. And of course, one of the things that we all know is that charges always radiate when accelerating. Accelerating charges always radiate. And that's a fact. So we are accelerating charges. Now, so essentially what you then have to do is a broadcast antenna in the transmitting antenna. So a broadcast antenna is specially designed to enhance the rate of electromagnetic radiation. So we know that charges radiate when they're accelerated. So the broadcast antenna is designed to especially enhance this rate of electromagnetic radiation. Okay, and so special shielding, special protective shielding must be employed to prevent radiation from going where you don't want it to go. You want to control where it goes. You also want to control where you don't want it to go. All right, and so now, so again, radiating charges in an antenna, or sorry, accelerating charges in an antenna radiate, right? Accelerated charges always radiate. Well, that's how your microwave oven works. If you imagine a microwave oven, again, we're going to talk about electromagnetic spectrum in a moment, but a microwave is another form of electromagnetic wave. Your microwave oven so your microwave oven sends electromagnetic waves from a concealed antenna. Where, of course, charges are accelerating. Charges are being accelerated. We'll talk about microwaves a little bit more in a moment, but again, you have a broadcast antenna in your microwave oven. Microwave oven is generating another kind of electromagnetic waves called microwaves. Again, we'll talk about this in a moment. Okay, so we now know we understand now how to broadcast or transmit electromagnetic waves. We also understand the concept of receiving electromagnetic waves. Now, as I said, there's when I was first talking about the transmission of electromagnetic waves, we know that there are the electromagnetic wave has an electric field vector whose magnitude and direction sinusoidally varies in time in one direction. I called it the y direction in my original example. Simultaneously, the electromagnetic wave has a magnetic field vector whose magnitude and direction and we'll say one dimension up here varies sinusoidally in time, but in phase with the electric field. And in a direction perpendicular to the electric field. The electromagnetic wave propagates dimension, I guess. Propagates in a direction mutually perpendicular to E and B at speed c, speed of light. These are all the things we know. Now, it turns out that when you have a wave propagating, it's going to have an amplitude, a maximum. It's going to have an amplitude. So let the electric field have an amplitude E naught, or I guess so. Yeah, E naught. So let's the electric field of the electromagnetic wave have amplitude E naught. Again, that's the maximum length of the vector in either direction, amplitude E naught. It's an amplitude. I'm not going to put a hat on it. And let the corresponding magnetic field have amplitude B naught. Then we state without proof that these amplitudes are always related by E naught over B naught equals the speed of light. So if you take the ratio of the amplitude of the electric field, that's an electromagnetic wave, divided by the ratio, divided by the magnitude of the or the amplitude of the electric field in the electromagnetic wave, divided by the magnitude of the magnetic field in the electromagnetic wave, you take that ratio is the speed of light. That's always the case. The two magnitudes of the electromagnetic waves are always related, and their relation is the speed of light. Again, I state that without proof. We're not going to prove that. I'm just going to literally write that down. This equation you can take to the bank. All right, E naught over B naught equals C. Okay, what I'm going to do now is work out some problems. So I'm going to do open stacks. Again, we're in chapter 24 of Cutnell Johnson, and we're also in chapter 24 of open stacks. So the chapters have realigned. They're out of alignment for a little bit. I'm going to look at open stacks 24.4. All right, that says the maximum magnetic field strength of an electromagnetic field long word here. Some people would say EM is 5 times 10 negative 6 Tesla. Okay, calculate the maximum electric field strength if the wave is traveling in a medium in which the speed of light, in which the speed of the wave is 0.75 C. Okay, the maximum magnetic field strength of an electromagnetic field is 5 × 10⁻⁶ Tesla. That's your B naught. Calculate the maximum electric field strength, that's your E naught, if the wave is traveling in a medium in which the speed of the wave is 0.75 C. That's your velocity, that's your speed, all right? And so again, I'm gonna erase the board here for real estate. This is just a direct application of the last equation I wrote down. And so, all right, so what that means is that the maximum magnetic field strength, we're told, is B naught, is 5 × 10⁻⁶ Tesla. We're told that we want to find E naught, the maximum magnetic field strength, or the magnetic field amplitude, if you will. And the speed is 0.75 the speed of light. So how do you do this? Well, you say, well, I go to the equation E naught over B naught equals V. Okay, again, the speed of light in a medium we'll find out when we talk about refraction. We talk about optics in the next chapter. We'll talk about the speed of light in a medium is actually less than what it is in a vacuum. All right, so this is still the speed of light. So essentially, I'm going to solve for E naught. So real simple algebra says that E naught is just V B naught, or E naught is 0.75 C B naught. E naught is 0.75. We'll just use speed of light right now of 3.00 times 10 to the 8th meters per second. This is an approximation for it. And then times B naught, 5 × 10⁻⁶ Tesla. That's only good to one sig big anyway. So E naught we'll find is about 1125 volts per meter. So if the maximum magnitude, if we understand that the speed of light in this particular medium is 0.75 C, and the maximum magnitude of the magnetic field is has a strength of 5 × 10⁻⁶ Teslas, then we can determine the maximum magnitude of the electric field is 1125 volts per meter. All right. So next thing I want to discuss is it's kind of more of a taking a walk through the electromagnetic spectrum. All right, and so what we see here is, a very beautiful whole new industry that just opens up with what we've been talking about. Many industries, in fact. So let me go back to sharing my my screen. So we have propagating electromagnetic waves. And give me a moment here. Now, they all, share my screen. Second. Okay, so electromagnetic waves can be described, essentially they all have a wavelength and a frequency. As I said, electromagnetic waves, what makes one different than the other is what is its wavelength and what is its frequency. And so we're familiar with light, visible light, but you notice that visible light is only a very small region, very small sliver electromagnetic spectrum. Electromagnetic waves range all the way for long waves, which would be long waves would be which would be slow frequencies or low frequencies, long waves, low frequencies, all the way up to radio waves, all the way to very short waves with very high frequency, which would be your X-rays and your gamma rays. So electromagnetic waves encompass everything that's on this diagram. Radio waves, a large portion are called radio waves. We'll talk about each one of these. And in fact, I'm going to talk through the electromagnetic spectrum from the very longest wavelengths all the way to the shortest wavelengths. We're going to kind of walk through the electromagnetic spectrum and get ourselves familiar with what the different aspects of our, we talk about these things in our regular lives, but do you know where they are in the electromagnetic spectrum? So you see a whole large region called radio waves. Well, radio waves are any waves that are in this particular, I would say, the top is wavelength and the bottom is frequency. So anything in this frequency regime would be radio waves, including AM radio, FM radio, and microwaves. All of these are part of radio waves, all right? And then you go and you have shorter wavelengths yet, higher frequencies, you go into what's called the infrared. That talks more about like heating and stuff. Then we have this very small sliver called visible light. And then infrared, actually, so visible light goes, Roy GB of Roy, red, orange, yellow, green, blue, indigo, violet. So it goes from red over to violet. Infrared literally means below red. So this region is, essentially some of it actually intersects with the microwave region. But this is the infrared region. You have a very small electromagnetic spectrum where all of our eyes are tuned to be to see visible. And then beyond visible, beyond the violet is ultraviolet. Ultraviolet literally means above violet. Okay, and then that's higher frequency, shorter waves. Yet even shorter waves, even higher frequency are X-rays, and then even shorter waves and even higher frequencies are gamma rays. All right, and so one of the things we can see is that well, let's kind of look at how these waves interact in our lives. All right, and so they all have aspects that are both good and bad in our lives. So there's a table here. This is table 24.1 of OpenStax. Okay, it goes through the spectrum just like I did, from long wave to short wave. You have the radio and television. Again, we'll talk. I'm going to walk through how this, how they're produced by accelerating charges. We just talked about that. We accelerated charges in an antenna, and we generated radio waves, and television, TV waves are within radio. You accelerate charges in a conductor, in an antenna. What are good applications? Communications, remote controls. Now, a lot of you, this book, by the way, as I've said before, the OpenStax book is actually written with care being given to life science majors. The book wants to teach you, real physics, but at the same time, it also wants to interest you in physics by showing you what are the applications for life sciences. So in that concept, in that spirit, we have life sciences aspect. So one of the life sciences aspect for radio waves is MRIs. What are some issues? Well, we have to have controls. We have to have organizations that control who goes on what radio band. So the issue is you're fighting for bandwidth. And certain bandwidth is restricted for military use. Certain bandwidth is AM. Certain bandwidth is FM. You can't just make an FM radio station that's outside of the official FM radio, except the radio bands. At the same time, you can't do an AM radio that's outside the AM radio bands. I mean, again, these are set aside by by agreed upon rules and restrictions. We go down to microwaves. Now we can get a microwave by accelerating charges as well, but we also can get them through thermal agitation. What are good for microwaves? Well, communication devices. Your cell phones run on microwaves. Ovens. Again, you have the microwave oven. Radar. Radar is also run off microwaves. Good medical use is deep heating. Deep heating of your muscle tissue. Issues, well, cell phone use. Cell phones. Cell phone use has actually created a challenge to our society. Not only do we have to have cell phone towers and more phone numbers for everybody, but there's also not or maybe possibly not understood environmental consequences to the large use of cell phones. Some people believe that it affects the honeybees, for instance. Infrared, to move up the spectrum. Again, how do you make them? Thermal agitation, electronic transition. So you can get them from a circuit, electrical circuit. You make infrared waves from a circuit. What are good applications? Thermal imaging, heating. Life sciences. Well, infrared gets absorbed in the atmosphere. What's an issue? Greenhouse effect. The greenhouse effect is radiation comes from the sun, gets trapped by carbon dioxide and water vapor, as it gets re-radiated off the earth, and it gets trapped in it, and it slowly increases the global temperature. We have the global warming effect. That's a greenhouse effect. We have a number of issues regarding that. Then we go to visible light. A small sliver of visible light. Again, you can get visible light from thermal agitations and also electronic transitions. Applications all pervasive. We live in a very beautiful, rich world, lit in the visible spectrum. What are good life science applications? Photosynthesis, human vision. Issues is blank. There's no real known issues with visible light. Your ultraviolet spectrum, you get it through thermal agitations, electronic transitions. Good applications would be sterilization and also cancer control, fights cancer. What are good aspects, life sciences? Well, it helps you produce vitamin D. What are issues? Ozone depletion. We'll talk about that. We're depleting our ozone layer. Also, it can cause cancer. Too much UV exposure causes cancer. Then you go to X-rays. Again, X-rays now, you can get them through, you get them through inner electronic transitions. So again, basically quantum transitions, electronic transitions in the atom. That's how you get X-rays. We use X-rays, of course, for medical and security. So X-rays are used, in the dental office, or used to look at your bones. And also, you can use it to look at your luggage at the airport, used in security. Life science, well, medical diagnosis, cancer therapy would be how you can use X-rays in life science. Issues, well, X-rays can cause cancer, right? Gamma rays, you get gamma rays from nuclear decay. The only way to get gamma rays. And we'll talk about alpha, beta, and gamma. Well, gamma is actually electromagnetic waves. Alpha and beta decay deals with certain particles. We'll talk about that in chapter 31. Applications, well, there's something called nuclear medicine. And again, they're used in security. Some airports actually use gamma rays to look at your luggage. Again, the gamma rays are very similar to X-rays. They're just more powerful and shorter waves, right? So same kind of applications. Medical diagnosis and cancer therapy, and the same issue would be, gamma rays can cause cancer, and also they can cause radiation damage. All right, so we have this whole long line of this wide range of electromagnetic spectrum and what its applications are to you. All right, and that gets me to, where I kind of want to walk through the electromagnetic spectrum a little bit, all right? And so, again, going from long waves, so first of all, let's talk about some general principles of an electromagnetic spectrum. Okay, so general principles, or observations, if you will. Again, this is regarding electromagnetic spectrum, and I call these, say, rules of thumb. Okay. Electromagnetic spectrum is the high frequency electromagnetic waves are more energetic than and are more able to penetrate at low frequency waves. That's one. High frequency electromagnetic waves can carry more information. Per unit time than low frequency waves. Again, a lot of our cell phone is off of microwaves, or they're again a higher frequency than, say, radio. Okay, and another rule of thumb would be the shorter the wavelength of any electromagnetic wave, probing a material the smaller the detail is possible to resolve. All right, so that's why you can't look at an atom with light, right? Because light has a larger wavelength than the size of the atom. You can only look at something with a wavelength, resolve something that has a wavelength that, your wavelength of light that you're looking at something, or whatever electromagnetic spectrum, is about the size of something you can look at. You can't see things that are smaller than the actual wave, electromagnetic wave, or the actual wavelength that you're using. That's number 3 says. So again, high frequency electromagnetic waves are more energetic and are more able to penetrate a low frequency than low frequency electromagnetic waves. Okay, so again, gamma rays, X-rays are far more energetic, far more penetrating to the body than, in fact, the only electromagnetic waves that actually do penetrate biological tissue is ultraviolet, X-ray, and gamma. Visible light will never penetrate your body, and anything with a wavelength greater than visible light will never penetrate your body. The only waves that'll penetrate you are ultraviolet, X-ray, and gamma rays. And again, ultraviolet, X-rays, gamma rays are much more energetic. High frequency electromagnetic waves can carry more information for unit time. So you want higher, denser information being carried, you use a higher frequency wave. So a lot of times, so you'd say your cell phone is based on microwaves. You can carry a lot more information on microwaves than say, and satellite information is carried on microwaves. You carry a lot more information on microwaves than you would on radio waves. Okay, and as I just said, the shorter the wavelength, I mean, basically the size of your wavelength is really the size of what you actually can study. All right, you can't study something that's smaller than the wavelength of the electromagnetic waves that you're using to try to study it. Now, one other thing to keep in mind with waves before we kind of go into the spectrum is that, and again, this is going to become more evident when we talk about optics. Electromagnetic waves, so when electromagnetic wave impinges on a material, it can reflect from the material, reflect off the material, transmit through the material, or be absorbed by material. And I'll say and or be absorbed. By the material. And sometimes a little of all happens. Okay? And so if the material is transparent at some frequency, most of the wave will be transmitted through the material. Okay, so and that brings up some interesting points, and also if a material is opaque, to an electromagnetic wave at some frequency, then the wave will be mostly reflected. Okay, and so you can have reflection, transmission, or absorption. So again, material is transparent. So again, when an electromagnetic wave impinges on a material, it can reflect off the material, transmit through the material, and or be absorbed by the material. If the material is transparent at some frequency, most of the wave will be transmitted through the material. If a material is opaque to electromagnetic wave at some frequency, then the wave will be mostly reflected. And thirdly, the wave can also be absorbed in a material. Right, and essentially when that happens, this would indicate that there's some interaction between the wave and the material. Such as thermal agitation of molecules, for instance. Energy is being absorbed. All right, so in general, it is possible to have partial transmission, reflection, and absorption at the same time. All right, so again, all three of these can be actually happening. So for instance, as I said, I mentioned I mentioned frequency. For instance, that the electromagnetic wave at some frequency, the material might be transparent, and another frequency, the material might be opaque. So for instance, give kind of a funny example here. So for instance, visible light, so glass, is ordinary glass, is transparent to visible light. Again, one set of frequencies. But opaque to ultraviolet radiation. I always sometimes hear about people being worried about getting a sunburn through their window. Well, you're not going to get a sunburn through your window. Because yes, you'll get the visible light through glass, but you'll not get ultraviolet radiation through glass. The ultraviolet radiation will be blocked by glass. Ultraviolet radiation is opaque to glass. It cannot go through glass. Visible light is perfectly well transparent. Again, it just depends on the frequency. Visible light is just electromagnetic waves at one frequency, and ultraviolet radiation is electromagnetic waves just at a higher frequency in the ultraviolet region, right? But through the atomic molecular interactions of the glass, visible light transmits fine. Ultraviolet radiation is, the glass is opaque to ultraviolet radiation. It reflects the ultraviolet radiation, which is a good thing for us. It means that we can drive around and not have a sunburn, with, inside, through the windows of our car. Okay, so now let's walk through the electromagnetic spectrum. And so, it's probably most important to us going all the way. Again, we're going to start talking about radio. Radio waves, as we recall, was the very longest waves of electromagnetic spectrum. All right, so radio and TV waves. Okay. So again, the broad category of radio waves is defined to contain any electromagnetic wave. Produced by currents and wires and circuits. So if your wave is produced by a current in a wire or a circuit, it is a radio wave. Okay, so again, the antenna that we talked about, we're talking about periodically alternating charges or a charge distribution antenna to create the electromagnetic waves. That is a radio wave. That is an example of a radio wave. Why? Because it is being produced by currents and wires and circuits. Any wave so produced is a radio wave. And so, the name derives from most common use. The name derives from its most common use, the radio. But microwaves are in this regime as well. Now, for instance, radio waves are also electromagnetic waves from any other source in this frequency range. So, for instance, some astronomers look at the universe through radio waves. So astronomers can study the universe by detecting radio waves. from astrophysical processes. Not from extraterrestrial radio stations, right? We're talking about processes that are in this particular band of frequency range, all right? So again, anything in this frequency range is a radio wave. So in the radio wave, within the radio wave are TV and also microwaves. Okay, and so radio waves include TV waves and microwaves. All right, so we look at probably the largest radio waves that we can possibly have. We start off, we call them ELF waves, ELF waves, for extremely low frequency. So we go all the way to the largest, longest possible waves, and we're going to go to try to go to the shortest wave. So we start off, and we have what are called the extremely low frequency, ELF. Okay, so those are the longest waves possible. They're generally on the order of, the frequency is on the order of about 1 kilohertz. All right, very long waves. They're used to communicate with submarines. So communicate with underwater submarines. Salt water absorbs electromagnetic waves very well. So very long wavelengths. Are needed to reach these submarines. All right, so that's the ELF. All right, then we go to AM radio. All right, so AM radio, probably none of you ever listen to AM radio, but again, AM radio is would be the next regime you would go to, AM radio. And AM stands for amplitude modulation. The AM band is officially between 540 and 1600 kilohertz. So 540 kilohertz to 1600 kilohertz. So if you look at your AM, if you look at your radio in your car, for instance, you would see that you could set stations from 540 to 1600 on the AM radio band. And again, that's because the official allowed band for AM radios between 540 and 1600 kilohertz. All right, and so the basic idea, show you a little picture here, is that you have a carrier wave that actually carries your information. Let me show you another picture. So actually, I'll show you a ELF wave first. Again, these are all pictures from OpenStax. Share my screen. All right. So you see the first picture you see here is that ELF radio wave, extremely low frequency radio wave. Basically, extremely low frequency since C equals lambda F. Extremely low frequency means very long, very large wavelength. So you have this wavelength that, you have an underwater submarine, because of the attenuation, officially it's called attenuation of electromagnetic wave in salt water or any other conductor. Conductors will attenuate or weaken electromagnetic waves very, very fast. And so in order to be able to reach an underwater submarine requires very long wavelength radio waves. Okay, now we talk about AM radio. Amplitude modulation. What does that mean? Okay, so this is a good picture that helps. The left picture talks about the carrier wave. The carrier wave is actually going to be the signal. And the modulation is essentially is that, so there's the carrier wave that contains the signal, then the audio portion is modulated via amplitude. The amplitude changes. And so essentially you multiply the carrier times the audio, you get, this is the convolved wave. This is the multiplied wave, the amplitude modulated wave. Okay, and so you essentially so you essentially will change the amplitude in that manner. The radio receiver is tuned to have the same resonant frequency as the carrier wave. So your radio receiver actually will have the same resonant frequency as a carrier wave to pick up the signal while rejecting any other kind of frequency. The circuitry is designed to respond to the variation in amplitude of the carrier wave. And again, it wants to replicate the original audio waves. You're replicating the audio signal so that you can oscillate your speaker or perhaps your recording. So again, as you see, the audio wave, so you have the carrier wave, you have the carrier, try to draw this out here, you have the carrier wave that has some signal, and then you have the audio that, so your audio is amplitude modulated. It's your AM audio. Again, that's just going to be a modulation of the amplitude. And then you essentially multiply these guys together, and what you get is the overall wave that you will get. You're going to get this shape, but inside of it is going to be the carrier wave. So again, you'll have a shape that's going to try to make it look symmetrical here. It's going to be symmetrical. My drawing is not that good. And inside of here is the confined carrier frequency, carrier waves. All right, and so what happens here is then that the carrier wave has the basic frequency of the radio station. All right, so the carrier wave carrier wave has contained, or has the basic frequency of the AM radio station. So, for instance, if you were tuned into 1530 kilohertz, say that's your favorite AM radio station, this is the frequency of the carrier wave, carries the information. All right. Now the receiver circuitry, so the audio wave is modulated, is amplitude modulated. And the receiver circuitry on your end is designed to produce an audio signal by moving the speaker in response to the amplitude modulation. All right, so again, the radio wave is modulated by amplitude. Your speaker, your circuitry on the receiver end responds to the amplitude modulation. Okay. And then we talk about the FM radio, which is probably what most of you listen to, and me as well. That's a different band. You have the FM radio. Now, FM stands for frequency modulation. All right, so what does that mean? Well, let's go show you another picture. All right, so what's happening now is that you have the basic carrier wave that's set to the frequency, the basic frequency of the radio station, and then you have the audio signal, the second wave, that has the same amplitude, but is at a different frequency. Again, the frequency is modulated. We multiply those two together, you see that you have the frequency. Sometimes it's less, sometimes it's sometimes it's higher, lower, higher, and it modulates the frequency when you have these two multiplied together. That gets the information across. You're not getting information across by modulating the the audio by modulating the amplitude anymore. Now the amplitude is the same. You're modulating the frequency. And so the frequency, and so essentially what happens is that, so the FM radio, you're confined to a different band. So again, the FM radio, you notice on your radio dial, it's confined to 88 megahertz to 108 megahertz. You turn into your favorite station, 105 or 93 or whatever your favorite radio station is. You're tuning into a particular frequency, carrier frequency of the radio station. So, for instance, if you tune into, let's say 105.1 is your favorite radio station, then the carrier frequency or I'd say the basic carrier frequency of the FM wave is 105.1. (105.1 megahertz). All right. Now, the amplitude, as I said, is a constant. Now, before AM, it's being modulated. The amplitude is changing. Here, the amplitude for FM waves is a constant. Okay. And so, now, for FM waves, the audible frequency range, the audible frequencies range up to 20 kilohertz. All right, or convert that to megahertz, 0.020 megahertz. All right, at most. All right, and so the frequency FM wave can vary from the carrier by as much as 0.020 megahertz. So the frequency can vary from the carrier by as much as 0.020 megahertz. All right, so that puts a limitation on how close these radio stations can be with each other. Okay, so again, you can't have a radio station any closer. So if you go to, there is a limitation to how close they can be, and again, there's and also how much from the carrier you can actually deviate, essentially. So moving on. So now the FM receiver on your end, you said to tune into an FM radio, is tuned to resonate at the carrier frequency, and when you tune your dial, you're resonating just like the Hertz experiment at the carrier frequency, trying to receive the same wave that is being sent out by that radio station. And has circuitry. That responds to variations in frequency. Reproducing the audio information. Just like, so reproducing the audio information. All right. AM radio, its circuitry responded to variations in amplitude, reproducing audio information. FM radio, the circuitry responds to variations in frequency, reproducing the audio information. All right, so that's how these the radios work. What about television? All right, so talking about television, television is also broadcast electromagnetic waves. Now, for television, television waves carry such a great deal of visual. They're also carrying visual information. So they carry such a great deal of visual and audio information. So there's so much visual and audio information carried on television waves that the channel requires a larger range of frequencies. Okay, so essentially each channel that you tune into requires a larger range of frequencies. A lot more information in a TV wave. All right. So TV channels range in 54 to 88 megahertz. So 54 megahertz to 88 megahertz. So just below the radio, or just below FM. And another range, 174 megahertz to 222 megahertz. So they actually have two ranges in which they operate, the TV channels, 54 megahertz to 88 megahertz. Remember, FM radio starts at 88 megahertz and 174 to 222 megahertz. All right, so now you can go beyond this. So again, remember the FM radio, going back a little bit, that went from, remember, 88 megahertz to 108 megahertz. It's a lot more dedicated to television. Now, you can also go even higher in TV, for instance. So again, again, there's two regions in television: the 54 megahertz, 88 megahertz, and then there the 174 to 222. The 174 to 222 we refer to as VHF. 174 megahertz to 222 megahertz is VHF. And you can imagine what that stands for: very high frequency. You can even go higher. You can go to UHF. UHF will take you from 470 to 1,000 megahertz. So 470 megahertz to 1,000 megahertz is UHF. That stands for ultra high frequency, not just very, but now we're in ultra high frequency. So, we're divvying up the electromagnetic spectrum for our own human purposes. All right. And on top of that, the TV video signal, I found this very interesting when I first read this. The TV video signal is AM. The TV audio signal is FM. So the video signal is amplitude modulated. The audio signal is frequency modulated. All right, and so, and again, this is from the ordinary TV from before. Now today we have satellite dishes, which even has higher frequencies, and now we have HD, high definition. So again, we are, we have the ability to have a tremendous number of channels at this point. We go to satellite. So hence why you have like a gazillion channels to choose from now. Now that everybody has satellite, we're not just limited to this range. Now we can even go higher. Okay. Now with all of this electromagnetic activity occurring, we have an issue with interference. Again, humans have completely taken over all the electromagnetic spectrum, and so now we have to kind of worry about, okay, we have to really have authorities that govern who gets what piece of electromagnetic spectrum, right? And so one of the things we have an issue with now is radio wave interference. And honestly, what you have is a problem of pollution. One of the things you have, I mean, that's what's, that people who are in the radio industry refer to this, So let's say, for instance, for example, astrophysicists want to study radio astronomy. However, there are competing radio waves. Not just from radio stations, not just from radio and TV, but also from remote controls. For, let's say, TVs and garage door openers. All of these are just producing yet more radio waves. All right. Sometimes, you know, so let's say, for instance, you go to a hospital or an airplane. So on, you know, at hospitals, and on airplanes, you're asked to turn off your cell phones. Well, the reason for this is that the reason is the 1.9 gigahertz radio waves, or you know, we'll say radio waves from your cell phones, can interfere with aircraft or hospital equipment, whatever the case may be. Aircraft or hospital communication equipment, or communication devices, we'll say. Right? Another space for one more word. All right, so again, that is the whole concept of radio wave pollution. You know, we have it so much that now we have to, you know, we're asked on aircraft and in hospitals to please don't use your cell phone. And the reason being is they're just trying to reduce the radio wave pollution. On an aircraft, it's a lot more important for the pilot to be operating the communication devices, or in a hospital, it's a lot more important for the doctors and nurses to be operating the equipment there than it is for you to be taking your cell phone call. All right, and so again, and so they're trying to reduce the amount of pollution. All right, the next radio wave that we could talk about are microwaves. And again, we're still talking about radio waves. This time we're talking about microwaves. Microwaves are also radio waves. Again, we're still in the broad category of radio waves and TV. Radio and TV waves. Those call it radio waves. That's the broad category in which we're still living right now. And the next subcategory is microwaves. Okay. Microwaves The microwaves are the highest frequency electromagnetic waves that can be produced by currents and circuits. So the microwaves are the highest frequency, you know, these are man-made waves, the highest frequency electromagnetic waves that can be produced by currents and macroscopic circuits and devices. It's the highest limit of what we humans can make through circuitry. So again, microwaves are the highest frequency electromagnetic waves that it can be produced by currents in macroscopic circuits and devices. All right. So again, this is going to basically finish off the radio wave section of electromagnetic spectrum. Since that is really the end of that's as much as we could possibly go. Microwave frequencies. Range from, and this again on the order of 10 to the 9th or a billion hertz to about 10 to the 12th or a trillion hertz. And that's roughly the region for microwaves. Now, again, since microwaves have the highest frequencies, F of radio waves, the broad category of radio waves, and we know that C equals lambda F, of course, always. Then they have the shortest wavelengths of these radio waves. And hence the name microwave. That's why they're called microwaves. They have the shortest wavelength. Micro. That's why they're called what they're called. Among all the radio waves, they're the ones that are the shortest. All right. Quotation marks. All right. So again, microwaves are the highest frequency electromagnetic waves that can be produced by currents and macroscopic circuits and devices. You can actually make these in circuits. They are the highest frequency electromagnetic waves that can be made from circuits. Okay, microwave frequencies range from 10 to the 9th hertz to about 10 to the 12th hertz. Microwaves are the highest frequencies. We know that, C equals lambda F. That means that of all the wavelengths, of all the radio waves, what we deem as radio waves, they have the shortest wavelength. Again, radio waves in and of themselves are what? They are electromagnetic waves that can be produced by circuits. Again, we saw this with the radio antenna, the transmitting antenna. So they're our very first example of a radio wave. Okay. Microwaves can also be produced by atoms and molecules. Okay, and so microwaves are a component. So microwaves are a component of electromagnetic radiation that's generated by thermal agitation. So thermal agitation generates microwaves. So microwaves are a component of electromagnetic radiation caused by thermal agitation. Okay, so thermal agitation will cause microwaves. So the thermal motion so the thermal motion of atoms and molecules in any object at a temperature above absolute zero causes them to emit and absorb radiation. All right, so again, that's where the thermal agitation comes into play. Now again, we go back to our rules of thumb is we use microwaves in communication devices as well. And so we can get microwaves from the natural world, from thermal agitation. Okay, what else is important about microwaves? Well, by that rule of thumb, since it's possible to carry more information per unit time on high frequency. So since high frequency, again, this was that rule of thumb, that I think was the third one. Since high frequency electromagnetic waves can carry more information per unit time. Right. Then microwaves are very suitable, or quite suitable for communication. All right, so for instance, most satellite is transmitted by microwaves. So most satellite and cell phone communication is via microwaves. All right, so again, very important in the communication industry. Okay, now, since one drawback is since microwaves have such relatively short wavelengths, they require a direct line of sight. They're not going to bend around things. So you can lose your cell phone communication, for instance. Okay. I guess line of sight from the transmitter to the receiver. So I have a mountain blocking away. Well, you're not going to get that communication. Okay. Also within the radio spectrum, well, no, again, speaking of microwaves still, our most common use of microwaves, I mean, I guess maybe our most familiar use of it is cooking food, right? We put food in the microwave. How does that work? So again, again, we deal with microwaves in many different ways. We see that they're very important in many ways, but for us, I think most of us, including myself, when we first think about microwaves, we think about food, all right? And so, essentially we use microwaves to cook food. Again, that's something that is, so microwaves, a microwave oven operates at 2.45 gigahertz. Operates at a frequency of 2.45 gigahertz. And which is produced by the accelerating, which is produced by the accelerating electrons in its concealed antenna. Transmitter antenna. There's a transmitter antenna within your microwave oven. It accelerates electrons, just like little radio wave example that I started off earlier in the lecture, and it generates electromagnetic waves at 2.45 gigahertz. And this creates an alternating electric field within the oven. All right, so water and some other constituents of food are polar, meaning they have a slight positive charge and a slight negative. Meaning they have a slight positive charge end and a negative charge end. Okay, so now so again, microwave oven operates at 2.45 gigahertz. That's produced by accelerating electrons in this concealed transmitter antenna. So it's giving off electromagnetic waves. Very similarly, that like your radio transmitting antenna does at your radio station. It creates an alternating electric field within the oven. The water and some other constituents of food are polar. It means they have a slightly positively charged end and a negatively charged end. All right, so I'm going to raise for real estate here. So we have food. Now what's going to happen now to these molecules? So the range of microwave frequency are so designed so that the polar molecules keep trying to orient themselves. They keep trying to reorient themselves with the alternating electric field. And in so doing, they absorb temperature. They absorb heat or energy which raises its temperature. it cooks the food. So they're constantly reorienting themselves. Overall, this is called dielectric heating. Remember we talked about dielectrics? Talk about a capacitor. Inside a capacitor is dielectric. Dielectric, the best dielectrics are polar molecules. Water would be an excellent dielectric. It's highly polar. So again, this is called dielectric heating because you are depending on the water molecule as well as constituents of the food to be polar molecules. If they were not polar molecules, microwaves would not work. So the energy is absorbed by the food, but not the plates. So the energy is absorbed by the food, but not the plates. Since the plate does not contain water. So it's really the water that really causes, that really makes things work. The water molecules. The plate itself does not get heated because it does not contain water. Okay. Now, sometimes you find out that if you don't spend enough time cooking your food in the microwave, you might get hot spots or cold spots. And those are caused by constructive and destructive places of constructive and destructive interference of the waves. So sometimes you find hot spots and cold spots in your food. Your microwave food. And this is due to regions, or due to the existence of regions of constructive and destructive interference. So microwave ovens with rotating turntables help reduce this issue. Or microwave ovens with rotating turntables help mitigate this problem. Or this issue. All right, so again, microwave oven, essentially the microwaves are so designed that they're in a good resonant frequency of the water molecules. So water molecules are going to constantly try to reorient themselves, and this motion of the water molecules allows the absorption of heat into the food. Okay. Now, another aspect of the radio waves as a whole is radar. You hear about radar. Radar is another area of radio waves. So radar is a common application of microwaves. Another common application of microwaves. Not just radio waves, but microwaves. And radar was first developed in World War II. Okay, and essentially, it's kind of is almost like the electromagnetic form of ultrasound to some extent, right? So essentially, you send off and you detect echoes. So by detecting and timing microwave echoes, kind of like you have sound echoes, well, here you have microwave echoes. By detecting and timing microwave echoes, radar systems can determine the distance of objects. The radar systems can determine the distance of objects as diverse as aircraft or rainstorms. All right. So a Doppler shift, we talk about Doppler effect, a Doppler shift in radar wave, in a radar echo, can be used to determine the speed of a car or the intensity of a rainstorm. All right. So again, the cop sitting on the side of the road uses a radar gun. He's bouncing an echo off of your car and determining how fast you're going. Weather system, weather services will use Doppler to determine the intensity of a bad storm, for instance. All right. And so again, microwaves are definitely used ubiquitously. In fact, microwaves are also used in space. As I said, there's radio telescopes. Well, there's some radio telescopes that look for microwaves. In fact, it was microwaves that gave us the first evidence of the existence of the Big Bang. So in 1964, so it was deep space. So deep space acts like a black body operating at 2.7 Kelvin temperature. And we talk about black bodies in physics 1. Talk about radiation heat transfer. So acts like a black body at a temperature of 2.7 Kelvin. All right. Now, so physicists like myself, we always like to dream about when we're going to have the great discovery in our careers, right? And it's always annoying when people trip over discoveries, right? They get the Nobel Prize and they're like, this happened at the right place at the right time, we're doing the right experiment. So this is an example of one of those. So in 1964, two gentlemen, I believe they work for Bell Labs, Penzias and Wilson. Penzias and Wilson detected the radiation. They detected microwave radiation everywhere they pointed their instruments. First, they thought, oh, this must be pollution from the city. So they moved wherever they went to do their experiment. They kept getting this hiss everywhere they went. This hiss of microwaves, and they eventually determined that this was radiation that from remnants of the Big Bang. So what they were actually determining was what at first of them was annoying. And it turned out to be one of the greatest things that ever happened to them. So they eventually recognized that this ever-present hiss was due to remnants from the Big Bang. So the Big Bang was a theory that did not have any evidence at that point until this experiment or this accident. We got our first evidence of the beginning of our universe, the Big Bang, all from a hiss of microwaves. Microwave radiation. This is called the microwave background radiation. It is everywhere. And Penzias and Wilson got the Nobel Prize for this. So sometimes, you trip over things, right? So anyway, this is not to take anything away. These guys are great scientists, but boy, it's It's a nice thing to happen. So anyway, you know, great discovery, one of the monumental discoveries about the beginning of the entire universe. All right. As we move on now, the next section of the electromagnetic spectrum. So we leave the radio section now, and we go to the next section. Electromagnetic spectrum is now infrared. All right. So now we're leaving the radio waves and the richness of what are in radio waves. The next section we go to now is infrared radiation, or IR. And so we're getting into shorter and shorter wavelengths, higher frequencies. So first of all, the microwave and infrared, sometimes this is referred to as IR. The microwave and infrared spectra overlap. First of all, okay, infrared radiation is generally produced by thermal motion of and vibration or rotation of atoms and molecules. So it is generally, so infrared radiation is generally produced by thermal motion of and vibration and the vibration or rotation of atoms and molecules. All right. We also can do through electronic transitions of atoms and molecules as well. So electronic transitions mean electrons going from one quantum state to another. We'll talk more about this in quantum mechanics, but electronic transitions in atoms and molecules can produce infrared radiation. And when I say electronic transition, this is an atom or molecule having an electron change from one quantum state to another, or change from a higher energy to lower energy quantum state emitting a photon. And we haven't talked about photons yet, but we'll say emitting a photon in the infrared region, we'll say. Infrared energy, or other say infrared region. We haven't talked about photons yet. We will get there in chapter 29. Anyway, that's what's going on. Electronic transitions. So the we also get a lot of infrared energy from the sun. So the sun provides electromagnetic waves in the infrared, visible, and ultraviolet. And about half of this, and about half is infrared. So about half of the, I'll say about half is infrared. The rest of it is ultraviolet and visible. So 50% or so is in the infrared. So again, that's a majority coming from the sun. We also have again this the solar radiation is the thermal radiation that we receive from the sun. We talked about that in physics 1. You know, there's heat transfer can occur as conduction, convection, and radiation. This is the thermal radiation that we're talking about in our heat transfer. Mostly infrared. Okay. So most of the infrared radiation so again, emitted from the Earth is absorbed by carbon dioxide and water in the atmosphere. With some radiating into space. All right, and so now I talked about this when we talk about radiation heat transfer. You know, we have this situation where you have the solar radiation coming into the Earth. Okay, so again, we have a situation where we have solar radiation meets the Earth's atmosphere. Some of this radiation is reflected back into space. Some is absorbed in the atmosphere. And some radiation reaches the Earth. Some of the radiation reaching Earth is reflected back into the atmosphere. So some of the solar radiation reaching the Earth is reflected back to the atmosphere and absorbed by carbon dioxide and water. The secondary reflection is called re-radiation. And is responsible for what's called the greenhouse effect. And talked about that in physics 1 as well. The greenhouse effect. So again, solar radiation meets the Earth's atmosphere. Some of the radiation is reflected back into space. Some is absorbed in the atmosphere, and some of the radiation reaches the Earth. Some of the solar radiation reaching the Earth is reflected back into the atmosphere and absorbed by the carbon dioxide and water contents in the atmosphere. The secondary reflection is called the re-radiation, that's responsible for the greenhouse effect. Now, the greenhouse effect is generally good. All right, and so if the greenhouse effect did not happen, Earth would be about 40 degrees Celsius colder than it is now. And life would not exist as we know it. So the greenhouse effect is generally a very good thing. However, here's where you hear about in the news. Many scientists have shown and it's not just speculation like, some people in the government want you to think it is, but many scientists have shown that the increased concentration of carbon dioxide And other greenhouse gases. In the atmosphere, resulting from increases in fossil fuel burning, resulting from increased burning of fossil fuels, has increased global average temperatures. Call that global warming. So in the original table I showed you, one of our problems with the infrared is, the greenhouse effect is, more than it really needs to be. So we're warming the planet a little bit too much. All right, that's the infrared. Now we go to a small sliver of electromagnetic spectrum called the visible light. And that's where our eyes generally work. All right, so visible light is next. All right, and so this is a narrow region of electromagnetic spectrum. From about 300 nanometers, or maybe 400, I think it's 300, to about 700 nanometers ish, maybe 750. In which the human eye responds. Okay, so visible light, how do we get it? Well, it's produced by vibration and rotation of atoms and molecules. So visible light is produced from vibration or rotation of atoms and molecules. And that's how we get visible light. And also, from electronic transitions. In atoms and molecules. So again, electrons changing quantum states. Sometimes they emit a photon in the visible. Okay. Actually, it's 400 to 700 nanometers. Apologize. So it's 400 to 700 nanometers, about 750 nanometers ish. So now 400 is basically violet. So essentially, light, the colors of light range from the longest wavelength, or we'll say the shortest wavelength, violet, or we're going from longer wavelength to shorter wavelengths, right? So we're shortening our wavelengths as we move across the spectrum. So from the longest wavelength, red, of about, let's say, 750 nanometers for red, to about 400 nanometers for violet. And the colors are ordered by, red. So you remember Roy G. Biv. Remember this guy, Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. Again, red, orange, yellow, green, blue, indigo, and violet. Sometimes they leave out indigo. From longest wavelength to shortest wavelength. Now, on one side of the electromagnetic spectrum, one side of the visible, we have the infrared, and the other side, we have the ultraviolet, right? So we'll talk about ultraviolet next. We just got done talking about infrared. Well, it's kind of funny, these names, right? So again, looking from long wavelength to short wavelength, long wavelength to shorter wavelength. Again, we have, what is it again? Roy G. Biv. Well, it's funny, we talked about infrared. Infrared means before red, I think it is. Double check that. Yeah, below red. We have infrared. Was that region that we talked about earlier? It really stands for below red. Infrared. So again, it's the part of the electromagnetic spectrum that has a wavelength that is longer than red. We just talked about it. We go to the other side of the electromagnetic spectrum, we'll talk about ultraviolet. So when we talk about ultraviolet, ultraviolet literally means above violet. Okay, so below red, above violet is ultraviolet. We're going to study after this chapter. We're going to, as I said, we're going to leave electromagnetic theory proper, and we're going to go into optics. We're going to study optics. The study of optics mainly involves visible light. So in chapters 25 and 26, we study what's called geometrical optics. So this is, so the electromagnetic waves in this regime, the electromagnetic waves have a wavelength much smaller than the objects and holes with which they interact. So that we can approximate the waves, the electromagnetic waves, as straight line rays. Chapter 27 is physical or wave optics. Where the above approximation cannot be made. You actually have to treat the electromagnetic waves as actual waves. All right, that's the visible spectrum. So as I said, after this is ultraviolet. Okay, now we go into shorter waves that are shorter than visible, and waves that can actually begin to penetrate biological tissue. And as I said, ultraviolet, its name means above violet. So we have ultraviolet, which we oftentimes call UV. Sometimes we refer to it as UV. All right, so again, ultraviolet means above violet. That's what the name means. The electromagnetic frequencies. So the So electromagnetic frequencies extend from that of violet light. Okay, and so now the so the existence of these of this radiation was recognized as early as 1801. By Johann Ritter. Now, solar radiation, solar ultraviolet radiation actually comes into three major categories. All right, and so we talk about UV radiation, but it really divides itself into three major categories. All right, so solar UV radiation is divided into three categories. All right, we refer to these categories as UVA, UVB, and UVC. So UVA, UVB, and UVC. UVA occurs in about 320 to 400 nanometers. So 300 nanometers to 420 nanometers. Or 400 nanometers, so just at the brink of violet light. Okay, UVB is about 290 nanometers to about 320 nanometers. And UVC goes to about 220 to 290. And so most UVB and UVC is absorbed by our ozone layer. So it's absorbed by the ozone. Ozone is basically an oxygen 3 molecule in our upper atmosphere. Okay, about 99% of the UV radiation is UVA. So the vast majority is UVA, but it's the UVB that causes the skin cancer. Now, the ozone protects that, right? All right, so again, we have UVA, UVB, and UVC. The distinctions are the ranges of the wavelengths of the UV radiation, And 99%, over 99% of all the UV radiation coming from the sun is UVA, which is actually quite a very good thing, of course. All right. Now, as I said, it is UVB that is linked to skin cancer in human beings. All right. Now, it's estimated that about 20% of all adults will develop some form of skin cancer in their life. Fortunately, if caught early, skin cancer is okay. So fortunately, if caught early, most people survive the skin cancer. Okay, again, the big thing is being caught early. Now, one of our problems, however, is in the southern hemisphere, an ozone hole is developing. And so again, ozone is what allows you to block the UVA and the UVC. The ozone hole is essentially, the ozone hole. Well, essentially, if ultraviolet radiation is the lowest frequency radiation, that can alter biological tissue. Okay, so that's where, because this is the first time in our electromagnetic spectrum we're encountering radiation that can actually alter tissue. Okay, and so this is why this is a bad thing to have too much ultraviolet or higher or shorter wavelength or higher frequency ultraviolet radiation coming to the Earth. So the UVB radiation The UVB radiation excites DNA molecules. And distorting the DNA helix. And that leads to mutations and possible formation of cancerous cells. All right. Now, also UVB, generally speaking, UVB exposure in humans leads to cataracts. In the eye. Again, this is about 60% of all people between ages 65 to 74 develop cataracts, which is like a clouding of the eye. Which requires the lens of the eye to be replaced by a plastic lens. So these surgeries happen all the time. But in equatorial regions, there's a lot of sunlight and there's a lot of poverty. Cataracts actually contributes to a lot of blindness. All right, so this is a large cause for blindness in equatorial regions. Oftentimes happen to be very poor. Another aspect of UV radiation is flash photography. Now, for instance, you might wonder, you go to an art museum, oftentimes flash photography is not allowed in your precious artworks. And colored prints. Because the UV radiation from the flash can cause photo degradation in the artworks. No flash photography. All right. So again, more application of UV. Now, the question is, what's going on with the ozone layer? You might have wondered, why is the ozone layer depleting? Why are we getting an ozone hole? All right, and so that's now this is interesting. Is that when I one of my degrees is mechanical engineering, and I actually had an internship for a refrigeration company, and at that time they were basically being given a dictate that they're no longer going to be allowed to use Freon, which is a chlorofluorocarbon that helps to deplete the ozone layer. They had to go and test replacement refrigerants. All right, and so again, there was a scaling back of refrigerants, and so a lot of this is that the ozone layer. The ozone layer is being depleted by what are called chlorofluorocarbons. Or short, they call them CFCs, which come from refrigerants. Like Freon. Nobody ever thought that you would stop using Freon. And also some foams. And what else? And some aerosols. So human usage of these chemicals help to essentially these chlorofluorocarbons get reduced released in the atmosphere and start forming chemical reactions. So a typical chemical reaction would be like here's a given chlorofluorocarbon situation. So let's say you have one of these CFCs, chlorofluorocarbons, CFCl3. Okay, so again, this is going to be a carbon, a fluorine, and 3 chlorines. Okay, are going to meet with light. Now again, light is given by HF. So HF is, we'll understand this in a little bit when we talk about photons. This is a photon of light. Okay, again, we haven't talked about photons yet. We can think of this as basically light. So essentially, a photon meets a chlorofluorocarbon. Okay, ozone hasn't even come into the picture yet. What happens after that is a photon breaks it up. So what you get is now CFCl2 plus a chlorine ion. All right, and then you get a second reaction. This chlorine that gets released can then meet up with an ozone. And that creates a ClO, chlorine oxide, I guess that is, plus a diatomic oxygen molecule. And you get another chemical reaction. The ClO that was just produced meets ozone as well. When that happens, you get another chlorine and you get 2 more diatomic oxygen. Now, what's the problem here? Well, first of all, you have a chlorofluorocarbon meeting light. Okay, so notice that you get the CFCl2 plus Cl. What's Cl do? The chlorine then meets with ozone, creates a ClO, plus diatomic oxygen. Well, the ClO also meets with ozone and creates yet another chlorine and two more diatomic oxygen. So what are the bad guys here? The chlorine and the ClO. Well, this first reaction with light produces a chlorine, and the chlorine meets with ozone, produces a ClO, and the ClO meets with ozone and produces yet another chlorine, which can again meet an ozone and break that ozone apart, and create another ClO, which meets ozone and breaks that ozone apart. And so again, you have this really bad reaction that quickly, and this reaction can occur for 2 years. One single chlorofluorocarbon can sit in the atmosphere before all this process, before all the havoc that it creates dies out. This can go on for 2 years. And so we have to stop, that this particular interaction from happening if we're going to keep life on Earth, quite frankly, because the ozone layer protects biological life. All right, and you see this. These are bad reactions, and these reactions they're a negative feedback. I mean, they're like a downward spiral. They beget themselves. The reactions themselves make themselves worse. The reactions not only break up ozone, but their byproducts break up ozone. All right, and so again, the CFCs are relatively stable. And can last in the atmosphere, can last about 2 years in the atmosphere. This is very scary. Okay, so now we have international concern, of course, over this. And so international concern created what was called the Montreal Protocol. So again, ozone, let's be frank about it. The ozone layer is necessary for biological life. Okay, we're not going to sugarcoat anything. The ozone layer is absolutely necessary. For biological life, not just humans, but any other animals as well. Due to its protecting us from UVB and UVC. Protection against UVB and UVC. Okay. International concern has created the Montreal Protocol. Where countries have promised to reduce CFCs, reduce and even eliminate use of CFCs, chlorofluorocarbons. So everybody has to be on on this. Right now, as of the writing of that book, our the OpenStax book, India is still the largest producer of CFCs at this point, or at least at the writing of that book. So all the countries have to get on board. Now, the Montreal Protocol looks to be working. That's the good news. Since we're seeing signs of recovery of the ozone layer. Fortunately, the United States has not pulled out of this like the Paris Accord for global war, for climate change. So hopefully, nothing happens that pulls us out of this too. UV light has benefits. It's all bad news. There's benefits to UV light, of course. So ultraviolet radiation helps vitamin D production. In fact, if you studies show that if you lack vitamin D production, or if you lack vitamin D, there are increased risk with different types of cancer. Including prostate, breast, and colon. So again, UV radiation helps again with vitamin D production. And again, for latitudes above 37 degrees, UVB is blocked all winter. So again, vitamin D production is really hard to have. To get enough UV radiation for vitamin D production is very difficult at the higher latitudes. So UVB is blocked by the atmosphere all winter long. Okay. You also use UV radiation is used to help infantile jaundice. And it's real simple. My daughter had infantile jaundice, and all you do is, you put her in a diaper, put her on a window out naked, and just in her diaper, and just let her get sunlight. And so again, that's how you handle the infantile jaundice. Again, it's UV radiation. Another good use of UV radiation is used for sterilizing workspaces and tools. Kills germs. It's a germ killer. Okay, so now if we go on from UV radiation, we go to what are called X-rays. We'll talk more about X-rays when we go into atomic physics. But going to the electromagnetic spectrum, the next place we'll visit is X-rays. Okay. So in the 1850s, some scientists such as Faraday working with high voltages or working with circuits with high voltages or high voltage discharge. Inadvertently or produce X-rays. They did not know about it. All right, and so the idea of an X-ray, it's basically X-rays are invisible, penetrating electromagnetic radiation. Okay, and so the name this high frequency electromagnetic radiation was called an X-ray because nobody understood what it was. Unknown. So because nobody at first understood what it was. All right. And so X-rays are generally caused by atomic transitions. and we'll study them in chapter 30. So X-rays are caused by atomic transitions, electronic transitions. X-rays overlap ultraviolet at their low frequency ends. Or say lower frequency end. They're definitely not low frequency. Okay. Now X-rays are more penetrating to living cells than are ultraviolet. X-rays are more powerful and more penetrating to living cells than ultraviolet. So they have some of the same problems. So exposure to X-rays can cause cancer, and genetic defects. But they can be used for cancer therapy. X-rays can also be used for cancer therapy. Okay, X-rays are used in medical field, of course. X-rays are used in the medical field. And this is called radiology. Okay, the last type of electromagnetic radiation that we saw in that spectrum is gamma rays. Oh, by the way, also X-rays can be used in security as well. All right, gamma rays. So gamma rays were first observed first detected in 1896. So gamma rays were first detected in 1896. Well, actually, nuclear radioactivity, I should say. Nuclear radioactivity was first detected in 1896. So nuclear, and again, this goes into chapter 31 physics. Nuclear radioactivity was first detected in 1896. So nuclear radioactivity came in three forms. And this will all be discussed in chapter 31. Alpha particles, beta particles, and gamma rays. So gamma rays, so we'll talk about alpha particles, beta particles in chapter 31, but basically gamma rays are the most powerful and highest frequency electromagnetic waves. So gamma rays are strictly created by nuclear radioactive or nuclear processes. So again, unlike other ones that like X-rays are determined by very the highest power electronic transitions, gamma rays are entirely determined by nuclear process, nuclear decay. So basically, nuclear decay, I would say. Nuclear decay, or well, I say nuclear. They can also be produced by nuclear weapons. It has to be nuclear. All right. So as you can see from the electromagnetic spectrum that I showed you earlier, the lower frequency gamma rays overlap with X-rays. So the lower frequency gamma rays overlap with X-rays. And like X-rays, gamma rays have their name because their origin was also initially a mystery. It did not know where they came from. So gamma rays are just like X-rays, except they have higher frequency and more power. Higher frequency and hence more power. So they do the same bad things that X-rays do, but worse. Okay. So gamma radiation is used in medical. So I mean, again, gamma radiation can cause cancer. And biological damage like X-rays. But they can be used in cancer therapy. All right. They also let's see, X-rays can actually be used to protect against food spoilage. You actually have X-ray treated foods. So X-rays can be, gamma rays can be used in prevention of food spoilage. Since they can kill microorganisms. But they also can alter the food. The gamma rays can also alter the food. And there's some controversy regarding the safety of eating, or the safety of ingesting gamma ray altered food. So that's a problem for some people. The other thing is X-rays, gamma rays are used. Gamma rays and X-rays are used by airport security. To analyze luggage. All right, finally, the entire electromagnetic spectrum, the one way or the other, is used in astrophysics. All right, so astrophysics uses the entire electromagnetic spectrum. Analyze the universe. Now, of course, we know we have the optical telescopes, but we have radio telescopes. An example is the Arecibo radio telescope in Puerto Rico. We also have the Parkes Observatory in Australia. Okay. We have infrared telescopes that have to be cooled with liquid nitrogen. The vibrations of the molecules in the antenna would be stronger than the signal being collected. So the thermal vibrations, thermal energy from because the thermal energy from vibrations in the antenna would be greater than the signal itself. If no cooling occurred. All right, so one such radio telescope is James Clerk Maxwell telescope in Hawaii. An example of this is the James Clerk Maxwell telescope. In Hawaii. All right. We also have many examples, of course, of optical telescopes. We have an ultraviolet telescope. Now, of course, we have to go into outer space for some of these telescopes. So, for instance, the Hubble telescope is ultraviolet. All right. And the Chandra X-ray Observatory was launched in 1999. So we have the X-rays, the Chandra X-ray Observatory. Was launched in 1999. That takes care of the X-rays, and then we have the gamma. So the gamma ray, the Fermi Gamma Ray Space Telescope was launched in 2008. So the Fermi, named after Enrico Fermi, the Fermi Gamma Ray Space Telescope. Now we're in the gamma rays. Because processes in the universe occur in the electromagnetic waves at the entire spectrum. So Fermi Gamma Ray Space Telescope was launched as recently as 2008. And it takes the place of the Compton Gamma Ray Observatory. And it will take the place of the Compton Gamma Ray Observatory, which lived from 1991 to 2000. Not sure what happened to it, but long range, the long and short of it is, astrophysicists use the entire electromagnetic spectrum to study the universe.